Hey everyone. For this one, we're still going to be using some of these online visualization tools. So if you want to have a look at this and kind of try these out yourself, these are in the celestial sphere notes, but we're still going to be using them for the next couple of sessions. So for this one, we're going to be talking about the seasons. And let's start by getting rid of a couple of misconceptions about the seasons. A lot of people think that the seasons are caused by annual variations in the distance between the Earth and the Sun. Sometimes the Earth is a little bit closer to the Sun. Sometimes the Earth is a little bit further away from the Sun because the Earth's orbit is slightly elliptical. It's true that the Earth is a little bit closer to the Sun at some times of year and a little bit further from the Sun at other times of year, but this is not one of the key causes of the seasons. In fact, Earth is actually closer to the Sun in January, when it's about 147 million kilometers away, and a little bit further from the Sun in July, which is when the Earth is at a distance of about 152 million kilometers. In fact, I tried to make this little graphic be to scale of the size of the Sun. The Earth is a little bit larger, but the size and shape of the orbit should be reasonably accurate. And notice there's a slight variation from when it's closest to the Sun and when it's further to the Sun, but it's not very much. Also, it's important to remember some of the patterns that you may have heard about with the seasons. When it is summer in the Northern Hemisphere, what season is being experienced in the Southern Hemisphere? When it's summer in the Northern Hemisphere, it's actually winter in the Southern Hemisphere, and vice versa. When it's winter in the Northern Hemisphere, it would be summer in the Southern Hemisphere. And if the variations of the seasons were caused by Earth's distance to the Sun, well, if the Earth was closer to the Sun, everyone would have higher temperatures. If this was what was specifically causing the seasons, if it was just due to the distance of the Sun, everyone would be experiencing the same seasons at the same time. So what is the cause of the seasons, if not the distance to the Sun? So again, distance to the Sun is not a significant factor in the seasons. What the seasons are actually caused by is the tilt of the Earth's axis as it orbits around the Sun. And it does this in two ways. The tilt of the Earth's axis and where it is in its orbit affects what are the angles that the Sun's rays are coming in and hitting different parts of the Northern and Southern Hemisphere with. And from that perspective on the Earth, how much time is the Sun above the horizon, or how much time is the Sun below the horizon? So the length of daylight. So let's try this in a couple of different ways. Let's start by thinking about the December solstice. So the solstice, let's introduce a little bit of terminology. We have two solstices. We have the June solstice and the December solstice. This is when the Sun reaches its very highest or its very lowest maximum height on the sky. So we've got the December and June solstice. Is when the Sun's max height reaches its lowest and highest values respectively. In December, the Sun is never going to get very high in the sky. In June, the Sun is going to be reaching its highest positions in the sky. And again, this is going to have some very important effects for the seasons. So if we look at the December solstice, as the Earth rotates on its axis, maybe I should start with this. I'm going to stop my share for just a minute. let's say we've got the Earth, and let's say this is the northern hemisphere, this is the southern hemisphere, and the Earth rotates on its axis, but that axis is tilted as this thing orbits around the sun. So, I'm going to pause this and set something up real quick. Like magic. So, let's say we've got the sun and we've got the Earth, and the Earth is rotating on its axis, but that axis is tilted compared to the plane that the Earth orbits the sun in. So, as the Earth rotates on its axis, there are going to be some points when the northern hemisphere of the Earth is tilted and looking a little bit more directly at the sun than the southern hemisphere is going to. So as the Earth rotates on its axis, when it's at this position in its orbit, the northern hemisphere is getting more direct sunlight. It can see the sun for a greater amount of time. So it's going to be summer in the northern hemisphere. Whereas the southern hemisphere, it's getting less direct sunlight. It's pointed away from the sun, and it's not going to be able to see the sun for as long. So it would be winter in the southern hemisphere. However, as the Earth orbits around the sun, so it goes over to this side, half an orbit later, now the southern hemisphere is getting more direct sunlight than the northern hemisphere is. The southern hemisphere is going to be able to see the sun in the sky for a longer portion of its day, for a longer portion of each 24-hour period than the northern hemisphere is experiencing. And again, as the Earth orbits around the sun, it's those two effects of the Earth is orbiting around the sun and the Earth's axis is tilted and always pointing in the same kind of direction. The Earth's axis that it's rotating on is always pointed in that kind of angle to the side direction as it orbits around the sun, still kind of pointed that way. And we're going to see how this is what gives the Earth its different seasons and how the seasons are different in the northern hemisphere and in the southern hemisphere. Voila, and the sun has magically moved to the corner over there. Okay. So let's see if we can identify a few more of the details of this and look at the differences between the December and June solstice. So in December, the northern hemisphere, due to the Earth's tilt, is kind of pointing a little bit more away from the sun, and the southern hemisphere is pointing more towards the sun. So in the southern hemisphere, the sun's rays that are coming in, those rays are really, really concentrated right around the Tropic of Capricorn. Whereas in the northern latitudes, more where Ohio is located, in these northern latitudes, the sun's rays, the same amount of sunlight is being spread over a larger region. And the sun is also never going to get very high in the sky. So in a location like Rio de Janeiro, the sunlight would be very, very concentrated. That same amount of sunlight is hitting a relatively small area, causing higher temperatures, causing the sun to be able to warm that region of the planet more rapidly. Whereas if you're in a location like Chillicothe, Ohio, that sunlight is being diluted a lot more. The same amount of sunlight coming in is distributed over a larger area. So each square meter of area does not get as much sunlight, resulting in not as much heating. What also happens is during this December solstice, the path that the sun takes across the sky is the shortest path, so it's the shortest day of the year, and it never gets very high in the sky. So the sun is never very high overhead. It's always coming in at this relatively low angle, which means the sun is able to heat up this region of the Earth not nearly as much as when the sun is higher in the sky. Okay. Let's see if we can map this out using this constellation map again. So I've set this to be December and let this run. Again, stars rise in the eastern half of the sky, set in the western half of the sky. And right around sunrise, when are we going to get it? Sunrise coming up right about Taking a little longer than I thought. There we go. The sun is going to actually rise a little bit south of east. Okay. The sun, all stars always rise in the eastern half of the sky, but it's not always going to be due east or rising due east or setting due west. When we talk about the sun rising in the east and setting in the west, the sun will rise in the eastern half of the sky and set in the western half of the sky. But in December, sunrise is a little bit south of east. And when we run this again, you'll notice that the sun takes this kind of looping path across the sky, but it never gets very high in the sky. I've set the latitude a little bit further north than I probably should have, but it'll be a decent representation. So it just takes this little short path across the sky. So let's try to draw that out a little bit. So for the December solstice, sun stays low in the sky. A short time of daylight, short amount of daylight. And the sun rises in the southeast and sets southwest. Now, I should highlight that the sun is low in the sky in the northern hemisphere. And a short amount of daylight also in the northern hemisphere, but this rises southeast and sets southwest. That's for everyone. So this is, again, kind of the same sort of map that I was showing in that little demo. Let's see if I can draw this decently well to see what this would look like. So if that's our horizon, this is the sky. I can do that a little bit better. Let's try that. Then the sun in December is going to take a path that looks something like this. So if this is east, west, north, and south, this is the path in December. And we'll fill in more of that as we go. Okay. What about in June, half a year later? Well, now, instead of the northern hemisphere being pointed away from the sun, the northern hemisphere is pointed a little bit more towards the sun. Locations near the Tropic of Cancer, that sunlight is very, very concentrated. If you're at a little bit more northern latitude, well, it's still a little bit more spread out than it is over the Tropic of Cancer, but still a lot more concentrated than it was in the December months. So in Mexico, you might get the very, very fully concentrated light. In a location like Chillicothe, Ohio, you might get just slightly diluted light. The path that the sun is going to take is going to be the highest location in the sky, be the longest amount of daylight, and everywhere the sun is going to rise north of east and set north of west. So let's try to simulate that. So let's say we go from December to June. So already we have over here in June, the sun is rising north of east. And if we run this, that sun is going to take, again, one of these looping paths around, but this one is showing up much, much higher in the sky than what we had during December in the northern hemisphere. So the sun is going on this path a lot higher across the sky. Notice it isn't getting directly overhead for these higher latitudes, but it takes this path across the sky, loops across, and it will eventually set a little bit north of west. So let's just wait a second as the sun is going across the sky and should be setting a little bit north of west. Yeah, so sets in the northwest for this part. So let me draw that part. So this would be the June path. And for this June path, the June solstice, the sun path is higher in the sky, highest in the sky. This is still, we're still assuming northern for this. Again, this pattern is flipped if you're dealing with the southern hemisphere. But for the northern hemisphere, the sun path is highest in the sky, longest amount of daylight. And the sun rises, sorry about that. The sun rises in the northeast and sets in the southeast. Sorry, sets in the northwest. My apologies. Rises northeast, sets northwest, and that one is for everyone. This one's north as well. And again, this is what causes those strong temperature variations, amount of daylight variations. It explains why the seasons are different in the northern hemisphere and the southern hemisphere. Again, this model is showing those details. One thing I want to mention about this term solstice, let's say we're starting in the December solstice where the sun is taking its lowest path across the sky. As the months go by, the path that the sun takes across the sky is going to get further and further, higher and higher in the sky until it gets that path for the June solstice. Solstice literally means sun stops. So as we go through April, then May, the sun is rising and setting higher and higher in the sky, and eventually gets to this June solstice where that pattern stops. And after the June solstice, now as we get into July, it's going a little bit lower in the sky. August, a little bit lower in the sky, and it kind of switches that position. Same thing for the December solstice. As we go through October and November, the sun is taking a lower and lower path across the sky until we get to that December solstice where it's at its lowest point. The sun stops getting lower, turns around, and starts going backwards. We've also got what are called the two equinoxes, the March and September equinox. And that would be when the Earth is in this location. The northern and southern hemispheres aren't really pointed towards the sun. They're not really pointed away from the sun. They're kind of perpendicular to that direction. And on these 2 days, the March and September equinox, everyone on Earth gets 12 hours of daylight, 12 hours of nighttime. Also, these are the only 2 days of the year where the sun actually does rise due east and sets due west. So I know I've heard lots of stories. I think if you've ever seen the show Lost, or I think in the Game of Thrones book, it talks about, oh, the weather's off and the sun isn't rising due east and setting due west. Sometimes it's a little north or a little south. There's a whole bunch of fantasy things that kind of use this as a trope. Yeah, the sun only actually does that twice a year. So, just a little kind of pet peeve of mine for that. So this path is the path that would be taken by the sun for the equinox. So that's the only day of the year where the sun actually does rise due east and set due west. And in fact, this is where the sun's path actually follows right along the celestial equator. As I mentioned before, it's important to note that when it's summer in the northern hemisphere, so longer days, more direct sunlight, sun is higher in the sky, it's winter in the southern hemisphere. So there would be shorter days, less direct sunlight, and the sun would be lower in the sky. and vice versa. Again, don't want to be, mentioning this every class, but flat Earth models fail to get both of those seasonal patterns to match up. Whereas this, spherical-ish Earth being tilted on its axis, it describes it pretty succinctly. One other kind of point, maybe this is a discussion question that someone wants to talk about or address. Quite a while ago, I read a report that more people have traffic accidents on the equinox than at any other time of the year. More traffic accidents occur with a greater rate on the March and September equinox than at any point during the year. Now, at first thought, this might be, oh, there's no way that could be true. But maybe something about how the sun is rising and setting and how that might affect traffic, maybe throw this up as a discussion question on how you think it could be plausible that there could be more accidents on the equinoxes, and how might you test, if you think you have a reason what might be causing that cars to have more accidents, then is there any way that you could test that? Any data that you could gather to try to see, your proposed mechanism for why cars might be involved in more accidents, or why drivers might have more accidents on these days? Is there any way that you could possibly test that? So maybe a discussion question. So let's try two thought experiments. So suppose that Earth's axis was tilted by 55 degrees instead of 23.5 degrees, but its rotation period, the amount of time it takes to rotate, and its orbital period, 365 days, were unchanged. Look through these questions and see if you can predict how the seasons would change if, again, all we did was just tilt Earth's axis more. So pause the video, try to work through these, and then we'll talk about them in just a moment. Okay, let's play around with this and see if we can get an answer. And I'm going to use this model to try to help us justify some of our answers. So we're saying, suppose the Earth's axis were more tilted, but the rotation period and the orbital period were unchanged. Would summers or winters be more or less severe than they are now? And specifically, the differences in temperature between summer and winter. Well, we said that the season was caused because the northern hemisphere is sometimes more tilted towards the sun, and at the other side of the orbit, it will be more tilted away from the sun. Well, if I increase that tilt, now on more of the northern hemisphere, the sunlight is even more direct on the northern hemisphere. Half a year later, now the northern hemisphere is not really getting any direct sunlight at all. So the summers would be more intense because more direct sunlight. Winters would be more intense because less direct sunlight. So the seasons would be much more severe. What about the regions around the North and South poles where the sun never rises? Would that be smaller or larger? Well, if I have this original tilt, notice as I'm rotating, there's a part on the top that always has a direct line of sight to the sun. Again, it's kind of hard to see on here. Let me move that up so it's not getting backlit. There's always a part that can directly see the sun all the time. If I tilt that even more, there's going to be an even greater area that always sees the sun, no matter how I rotate this around. And on the other side, there's going to be a much larger area that never gets to see the sun. All these areas over here, as the Earth rotates on its axis, none of these places are getting any direct sunlight at all. So the Arctic and Antarctic circles would be significantly larger than they are right now. What about the length of each season? Equinox to solstice or solstice to equinox? Would that be shorter or longer? Well, if we go back to this diagram, if all we do is increase the amount of tilt, going from December to March is still going to be 3 months. Going from March to June is still going to be 3 months. June to September, 3 months. September to December, 3 months. So if all I've done is change the tilt, the amount of time it takes that thing to orbit around the sun, that hasn't changed. So for this one, would the lengths of seasons be shorter or longer? In this case, there would be no change. The last one, would Polaris still be our North Star? With the actual tilt of the Earth, Polaris is right above our North Celestial Pole. So if this is the direction of the North Pole, or of that rotation axis, Polaris is right in that direction. If I tilt this even more, well, now the North Pole is pointing at some other star. So Polaris would no longer be our North Star, it would be some other kind of star. Let's try the next one. So let's go back to our original Earth. So we've got our orbital axis, our tilt. Let's say the Earth was somehow, instead of orbiting it at 1 AU, we moved the Earth so it was further away, and the Earth now takes 2 years to do a full rotation around the sun. If we've got the same axis tilt and the same rotation rate, how would we answer this same set of questions? So take a moment, try to go through those questions, pause the video, and then we'll talk about those in just a moment. Okay, so for this first one, would summers and winters be more or less severe than they are now? Again, I want to focus on the differences between summer and winter, because if the Earth is 50% further away, well, it's going to be colder for everyone. Colder summers, colder winters. I know I said that the distance from the Earth to the sun doesn't have a primary effect, but if we're increasing the distance by 50%, that's a lot more significant than the differences due to the eccentric orbit of the Earth. So we could probably say that summers are going to be colder, winters are going to be colder, but if the tilt's the same, well, we've got a bit of we've got the northern hemisphere a little bit more pointed towards the sun. Half a year later, it's pointed a little bit more away from the sun. Those two effects would be pretty similar to what we have right now, the differences between summer and winter. Again, both are going to be colder, but the differences aren't going to be as much. There would also be a bit of an effect because if it's orbiting at a greater distance and it's a slower orbit, it's taking a longer time, you're going to be in that summer months. You're going to be spending more time in that summer configuration and then more time in the winter configuration. That would actually cause the seasons to actually be a little bit more severe, but that would be kind of a secondary effect. What about the Arctic and Antarctic circles? Well, if we have the original Earth, there's a region that can always see the sun in the summer and that can never see the sun in the winter months. If I just took this system and just moved it further away, that region that always sees the sun, that Arctic Circle region, that's not really going to change if I just move closer or move further away. So the Arctic and Antarctic circles would actually stay exactly the same as they are right now. What about the length of each season? Well, going back to this, we're saying the orbit is a lot larger and it takes 2 years to actually make 2 of what we call a year of that time period. It would take that long, it would take much longer to make this orbit. So in this case, going from December to March, that would take longer. Going from March to June, that would take longer. So the length of each season, equinox to solstice, solstice to equinox, would be longer because it's now taking the Earth a longer time to orbit the sun. Lastly, would Polaris still be our North Star? Let me get this one out of the way. Would Polaris still be our North Star? Well, let's think about it. We've got the Earth its axis is pointing in that direction, but we're increasing the size of the orbit. We're moving it this way. So is the North Pole still pointing in that same direction? In order to answer this, you have to think about how far have I moved the object compared to how far away is the object that I'm looking at. Okay? So how far have we moved the Earth, about half an Earth orbit radius, compared to the distance to Polaris? Well, Polaris is so far away that just moving it to the side back and forth a little bit is not really going to change the angle to Polaris. It would be like if I said the city of San Diego, California, is approximately in that direction. If I move over here, it's still approximately that direction. I haven't really had to move my hand back and forth very much to compensate for that effect. In the same kind of way, just moving the Earth's orbit out a little bit further, as long as I didn't change the tilt angle, it's still basically going to be aimed at Polaris. So Polaris would still be our North Star in that one. So just to finish things off with this session, the main ideas for the seasons are that the seasons are caused by the tilt of the Earth's axis as it orbits the sun. This determines the angle of the sun in the sky. Higher angle is more direct sunlight. Lower angle is less intense light. So in June in the northern hemisphere, the sun's higher overhead and we're getting more direct sunlight. In December, the sun isn't as high in the sky and we're getting less direct sunlight. It also affects the length of time that the sun is in the sky for. Notice that the length of this path for June that the sun takes across the sky is a lot longer than this path that it takes in December. If it's a longer path along the sky, it's going to be in the sky for a longer amount of time. And again, we can kind of map out some of these patterns and say, well, where is the sun going to be going across the sky? During the equinox, the sun would actually follow the celestial equator. And because the tilt of Earth's axis is 23.5 degrees, that results in the sun always being within 23.5 degrees of the celestial equator. Again, in order to get a better or a little bit more familiar with the geometry of this, I do recommend having a look at this constellations thing, so you can say, well, what happens at different latitudes, what happens during different months, and when you run that, it'll kind of show how the sun moves across those different locations at each of those locations, at each of those times. So yeah, so in April, you can say, well, the sun's going to be taking this particular path across the sky, and we can compare that with, kind of interpolate between what's happening during the equinoxes and the different solstices to figure out, well, what would be happening in those intervening periods. So we'll call that good for talking about the seasons, and the next one we're going to be looking at is the phases of the moon.